In the time it takes you to blink, light travels 300,000 kilometers. In that single instant, a photon could circle Earth 7.5 times, and yet there are particles of light reaching your eyes right now that began their journey when the universe itself was just a baby, 13.8 billion years ago. We think of light as instantaneous. Flip a switch, and darkness vanishes. But what if I told you that everything you see in the night sky is a fossil? What if the stars above you are already dead? The galaxies you glimpse through telescopes no longer exist where you see them, and the most ancient light touching your skin carries secrets from before Earth, before the sun, before any star had ever lived and died. How can light that moves so impossibly fast take longer to reach us than our planet has existed? Join me as we embark on the ultimate journey through space and time, following ancient photons across the most unimaginable distances ever conceived. We're about to discover that the universe isn't just bigger than we imagine, it's bigger than we can imagine. Before we dive into this cosmic odyssey, let me know where in the world you're watching from and what time it is for you right now. Drop it in the comments below. I love seeing our global community of space explorers come together. To understand the universe's true scale, we first need to grasp something that seems simple, but is actually mind-bending. The speed of light isn't just fast, it's the ultimate speed limit, written into the fabric of reality itself. Picture this: 299,792,458 meters per second. That's light speed, and it sounds like just another big number until you realize what it means. In 1 second, light travels a distance equal to going around Earth's equator 7.5 times. In 1 year, that same relentless pace carries light across nearly 10 trillion kilometers, a distance we call a light year. But here's where it gets interesting. Light doesn't choose to go this fast. It has no choice. Every photon, from the moment it's born in a star's core to the instant it strikes your retina, travels at exactly this speed through empty space. Not faster, not slower, never accelerating, never decelerating. It's like the universe has a cosmic speed limit posted everywhere: 299,792,458 meters per second. No exceptions. This isn't just a quirk of physics, it's the fundamental heartbeat of reality. When Einstein revealed that space and time are woven together into space-time, he showed us that this speed limit isn't really about light at all. It's about how fast information, causality, and change itself can ripple through the universe. Light just happens to be massless, so it naturally travels at this cosmic speed limit. Like just a hafras with your cosmic speed limit. It's about how fast information för recivin the sprayer mine. Think about what this means. When you see lightning and count the seconds before thunder, you're measuring how much slower sound is than light. Light from that lightning bolt reached you essentially instantly, while sound crawled toward you at a mere 343 meters per second. But on cosmic scales, even light, the fastest thing possible, becomes almost laughably slow. Here's the revelation that changes everything. Because light has a speed limit, it also has a travel time. And travel time means that when we look out into space, we're not seeing what's there now. We're seeing what was there when the light began its journey. Every photon is a time traveler, carrying a timestamp from the moment and place of its birth. This transforms every telescope into a time machine, and every star into a historian. The deeper we look into space, the further back in time we see. Distance and time become two ways of measuring the same thing, creating what astronomers call look-back time. This simple concept, that light takes time to travel, is about to take us on the most incredible journey through space and time ever imagined. The speed of light isn't arbitrary. It's woven into the mathematical structure of space-time itself. But why this speed? Why not faster? The answer reveals something profound about the universe's design. Einstein discovered that as anything with mass tries to approach light speed, something extraordinary happens. Its energy requirements become infinite, literally infinite. You could harness the entire energy output of all the stars in the observable universe, and it still wouldn't be enough to push even a single proton to light speed. This isn't a technological limitation, it's a fundamental law of physics. Mass and energy are interchangeable, as Einstein showed us with E=mc². As you accelerate an object, you're not just making it move faster, you're adding energy to it, which according to relativity increases its effective mass. The closer you get to light speed, the more massive the object becomes, requiring ever more energy to accelerate it further. Only massless particles like photons can travel at light speed, and they have no choice. They must travel at exactly this speed. They can't slow down. They can't speed up. From the moment of their creation to their absorption, they exist in a state of eternal motion at the universe's speed limit. But here's the beautiful paradox. From a photon's perspective, its journey takes no time at all. Due to time dilation at light speed, time essentially stops. A photon that travels 13.8 billion light-years across the universe experiences no passage of time during its journey. It exists simultaneously at its moment of creation and absorption. This speed limit creates what physicists call the light cone, the absolute boundary of what can influence what in the universe. Nothing can send information, energy, or influence faster than light. This means that events happening right now in distant galaxies literally cannot affect us until their light has had time to reach us. The universe, in essence, has a communication delay built into its very structure. This delay is what allows us to see the universe's history preserved in the light around us. Every photon tells a story, and the universe is broadcasting billions upon billions of these stories simultaneously. Right now, ancient light from every era of cosmic history is arriving at Earth, carrying news from the past, like messages in bottles cast into an ocean of space. Consider the light hitting your face right now from the sun. Those photons began their journey about 8 minutes and 20 seconds ago in the sun's core, where hydrogen atoms fused into helium in a process so violent it creates temperatures of 15 million degrees Celsius. But even that's not the whole story. Those photons actually began as gamma rays deep in the sun's core, and it took them between 10,000 and 170,000 years to random walk their way to the sun's surface, bouncing off particles countless times before finally escaping into space for their 8-minute sprint to your eyes. When you look at the sun, you're seeing it as it was 8 minutes ago. If the sun suddenly vanished, you wouldn't know for 8 minutes. Not only would you still see it shining, but Earth would continue orbiting normally until the absence of the sun's gravitational influence, which also travels at light speed, reached us. This time delay becomes more dramatic as we look deeper into space. The bright star Sirius, the jewel of the winter sky, shows us what it looked like 8.6 years ago. The light from Polaris, our North Star, left that stellar beacon around 433 years ago, when Shakespeare was writing Hamlet. The Orion Nebula, that fuzzy patch visible to the naked eye in Orion's sword, glows with light that began its journey around 1,300 years ago, during the height of the Maya civilization. But this is just the beginning. Modern telescopes can capture light that's been traveling for billions of years, showing us galaxies as they existed when the universe itself was young. We're not just seeing old light, we're seeing the universe at different ages, witnessing cosmic evolution in real time. This creates an extraordinary situation. The night sky is actually a time machine display. Look up, and you're simultaneously seeing different eras of cosmic history. The nearest stars show you the universe as it was years ago. More distant stars reveal decades or centuries past. Nearby galaxies show you millions of years of history, and the most distant objects visible to our best telescopes show us the universe as it appeared billions of years ago, when it was radically different from today. Every astronomical observation is an act of archaeology. We're not studying distant places, we're studying distant times. The universe has preserved its own history in light, creating a vast library written in photons, and we've learned to read this cosmic chronicle. This profound realization that distance equals time in astronomy means that understanding the universe's size requires understanding its age. As we journey outward in space, we simultaneously journey backward in time. The most distant light we can see has been traveling toward us since the universe was just 380,000 years old, less than 3% of its current age. We're about to follow this ancient light across distances so vast that they challenge the very limits of human comprehension. Our journey begins with familiar territory, the modest distances within our own solar system, before expanding outward into the cosmic abyss. Each step will reveal not just how big the universe is, but how old the light around us truly is. Let's start our cosmic journey with the familiar, using light as our measuring stick for distances that, while vast by human standards, are mere baby steps on the cosmic scale. When you look up at the full moon on a clear night, you're seeing light that left the lunar surface just 1.28 seconds ago. In cosmic terms, this is practically instantaneous, close enough to real time that NASA's mission controllers could have near-normal conversations with Apollo astronauts with just a brief, noticeable delay. But even this tiny delay tells us something important. The moon, our closest celestial neighbor, sits about 384,400 kilometers away, light, traveling at its relentless pace of 299,792,458 meters per second, needs over a full second to bridge this gap. For the first time in our journey, we encounter the concept that even light, the fastest thing in the universe, takes measurable time to travel astronomical distances. Ythoe, it's Sefendario Kangelion BT and Nidri. Now, shift your gaze to the sun, that brilliant disk that dominates our daytime sky. The warmth you feel on your skin left the sun's surface 8 minutes and 20 seconds ago. This means that the sun you see is always the sun, as it existed more than 8 minutes in the past. When ancient civilizations worshipped the sun as a god, they were literally worshipping light from the past. This 8-minute delay has profound implications. If the sun were to suddenly double in brightness or dim significantly, we wouldn't know for over 8 minutes. Any solar flare, any coronal mass ejection, any stellar hiccup reaches Earth as a complete surprise, delivered by light that's been racing toward us across 150 million kilometers of empty space. Il Corv, Cether. This distance from Earth to the Sun is so fundamental to astronomy that it has its own name, the astronomical unit, or AU. It's our first cosmic yardstick, and it immediately shows us how vast nearby space really is. Light takes 8 minutes to cross 1 AU, a distance so large that if you could drive a car at highway speed without stopping, it would take you over 100 years to reach the sun. But we're still in our cosmic neighborhood. Venus, when it's closest to Earth, shows us light from about 2.3 minutes ago. Mars, depending on where it is in its orbit, can show us light anywhere from 4 minutes to 24 minutes old. Even our planetary neighbors are separated by light minutes of space. These seemingly modest delays are our first hint at a profound truth. In space now doesn't exist. There is no universal now that connects distant objects. Everything we see happened in the past, and the further we look, the deeper into the past we're peering. Even in our own solar system, we're beginning to see the universe's history preserved in light. As we venture beyond the inner planets, the delays grow longer, revealing the vast emptiness that characterizes our solar system, and indeed, most of the universe. Jupiter, the giant of our solar system, shows us light that's between 33 and 54 minutes old, depending on where Earth and Jupiter are in their respective orbits. When Galileo first turned his telescope toward Jupiter in 1610 and discovered its 4 largest moons, he was seeing a dance of worlds that had actually occurred nearly an hour earlier. Saturn, with its magnificent rings, delivers light that's 1.3 to 1.7 hours old. The beautiful images from the Cassini spacecraft, which orbited Saturn for 13 years, were always showing us Saturn as it existed over an hour in the past. Every command sent to Cassini had to account for this delay, with engineers planning maneuvers based on where Saturn would be, not where they saw it. Uranus pushes us into the realm of truly ancient light for our solar system anyway. Light from this distant ice giant takes 2.7 to 3 hours to reach Earth. When William Herschel accidentally discovered Uranus in 1781, He was seeing light that began its journey when the afternoon was just beginning on the other side of Earth. Neptune, the most distant planet in our solar system, shows us light that's 4 to 4.7 hours old. When you look at Neptune through a telescope, you're seeing it as it appeared when most people were just starting their day or finishing lunch. The light reaching your eyes began its journey across our solar system, while you were living a completely different part of your day. But planets are just the solar system's landmarks. The real revelation of our solar system's scale comes from understanding the space between these worlds. If Earth were a marble, the Moon would be a ball bearing 7.3 meters away. On this scale, the Sun would be a sphere 2.7 meters across, located 288 meters away. Mars would be another marble, about 440 meters away, and Jupiter, a larger marble, would sit 1.5 kilometers distant. Even on this dramatically reduced scale, our solar system stretches for kilometers. The space between worlds is so vast that it's mostly nothing, a few atoms per cubic centimeter, making it emptier than the best vacuum we can create on Earth. This emptiness means that when we send spacecraft to other planets, they spend most of their journey in absolute void, guided by the faint gravitational pulls of distant worlds. Voyager 1 and 2, launched in 1977, spent decades crossing this emptiness, and their radio signals now take over 22 hours to reach Earth from beyond the edge of our solar system's influence. The scale we're exploring, light hours across our solar system, is already challenging human intuition. We're dealing with distances so vast that light itself, the fastest possible messenger, takes hours to cross them. And yet, we haven't even begun to explore true cosmic distances. Our entire solar system, vast as it seems, is just a tiny speck in the cosmic ocean, invisible from even the nearest stars. At the edge of our solar system lies a boundary that few people know about, but which represents humanity's first tentative step into interstellar space. The heliopause, where the solar wind meets the interstellar medium, sits roughly 18 billion kilometers from the Sun, so far away that light takes about 17 hours to cross this distance. Voyager 1 crossed this boundary in 2012, becoming the first human-made object to enter interstellar space. When it sends back data about this alien realm, the radio signals traveling at light speed take nearly a day to reach Earth. We're commanding a spacecraft using light that's almost a day old, in a region of space where the Sun's influence finally gives way to the galaxy itself. But even this incredible distance, the edge of everything the Sun controls, is minuscule compared to what lies beyond. The Kuiper Belt, home to Pluto and thousands of other icy worlds, extends to about 50 AU from the Sun. Light from these distant frozen realms takes about 7 hours to reach us. The Oort cloud, a theoretical shell of comets surrounding our entire solar system, may extend up to 100,000 AU away, nearly 2 light-years from the Sun. This is where our journey takes a dramatic leap. We're about to leave light hours and light days behind and enter the realm of light years. The jump from our solar system to the nearest stars isn't just a change in scale, it's a change in the fundamental nature of the distances we're dealing with. To understand this leap, imagine shrinking our solar system down until Earth's orbit around the Sun is the size of a US quarter. On this scale, Pluto's orbit would be about 2 meters across, and the heliopause would extend about 5 meters from the center. The nearest star, Alpha Centauri, would be another quarter, located 1,100 kilometers away. This comparison reveals the true nature of our cosmic neighborhood. Even our nearest stellar neighbors exist in a realm so distant that light, the universe's ultimate speed limit, takes years to bridge the gap. We're about to enter a domain where the delays we measure aren't in minutes or hours, but in years, decades, centuries, and eventually billions of years. The ancient light we've been following, is about to show us its true age in our solar system. We dealt with light that was minutes or hours old. Beyond our solar system, we'll encounter light that's older than human civilization, older than complex life on Earth, and eventually older than Earth itself. Our cosmic journey is accelerating, and the universe is about to reveal distances so vast that they'll challenge everything we think we understand about space and time. The leap from our solar system to the nearest stars represents one of the most dramatic scaling jumps in all of science. We're about to enter a realm where distances are so vast that they're measured not in light hours or light days, but in light years. Distances that light, traveling at the ultimate cosmic speed limit, takes years to cross. Alpha Centauri, our nearest stellar neighbor, sits 4.37 light-years away. This means that when you look at Alpha Centauri through a telescope, you're seeing light that began its journey 4.37 years ago. You're literally seeing this star system as it existed over 4 years in the past. If Alpha Centauri exploded today, we wouldn't know until 2028. To grasp this distance, consider that light from Alpha Centauri has been traveling toward Earth since before the most recent US presidential election. During that photon's journey, entire seasons have changed, political landscapes have shifted, and personal lives have been transformed. Yet from the photon's perspective, the journey was instantaneous, a consequence of Einstein's time dilation at light speed. But what does 4.37 light-years actually mean in terms we can comprehend? It's roughly 41 trillion kilometers, a number so large it becomes meaningless without context. If you could travel at the speed of our fastest spacecraft, New Horizons, which reached Pluto in 9 years, it would take about 78,000 years to reach Alpha Centauri. That's longer than modern humans have existed as a species. Even more humbling, if we could travel at 1% of light speed, a velocity that would require technology far beyond anything we currently possess, the journey to Alpha Centauri would still take 437 years. The people who began such a journey would be long dead by the time their descendants arrived, and the civilization that sent them might have risen and fallen multiple times. This reveals something profound about interstellar space. It's not just big, it's empty beyond imagination. The space between stars is so vast and so devoid of matter that it makes our solar system's emptiness seem crowded by comparison. In interstellar space, you might find 1 atom per cubic centimeter, a vacuum more perfect than anything we can create in Earth's laboratories. Alpha Centauri itself is actually a triple star system, consisting of Alpha Centauri A and B, 2 stars similar to our Sun that orbit each other, and Proxima Centauri, a small red dwarf that's technically the closest individual star to Earth, at 4.24 light-years away. Unimaginably. Så du mulighederi, så vi find at vi 4 spiri a su for find to 4, so we find spiri vorth. Proxima Centauri has become famous in recent years for hosting Proxima Centauri b, an Earth-sized planet in its habitable zone. The light from this potentially habitable world, if it indeed exists as we think it does, began its journey to Earth before the COVID-19 pandemic began. Any radio signals that hypothetical aliens on Proxima b might have sent us would take 4.24 years to arrive, and our response would take another 4.24 years to reach them. A simple hello exchange would take nearly a decade. This communication delay illustrates why the speed of light isn't just an abstract physical constant, it's the fundamental limitation on how quickly information can travel through the universe. Even if we could send messages at light speed, interstellar conversation would be impossibly slow. The universe has built-in delays that make it inherently mysterious and unknowable in real time. The light from Alpha Centauri, connecting us to our nearest stellar neighbors, carries another profound message. We exist in a galaxy of isolated islands of matter, separated by unimaginably vast oceans of emptiness. The stars in our night sky aren't a neighborhood. They're distant beacons scattered across a cosmic wilderness, each one a solitary outpost in the infinite dark. Yet even this isolation has a beautiful consequence. It means that every star system develops and evolves independently. The diversity we see in stellar types, planetary systems, and potentially even life itself emerges from this cosmic isolation. The universe's vast scale doesn't just separate us from other worlds, it allows countless different worlds to exist. As we prepare to venture deeper into the stellar neighborhood around our Sun, we'll discover that even stars we think of as nearby show us light from years, decades, and centuries past. We're about to see how the night sky itself is a museum of stellar history, with each star frozen in time, at the moment its light began, the journey to our eyes. Within 20 light-years of Earth lies a collection of about 130 stars that astronomers call our local stellar neighborhood. These are the stars that would be visible from any planet orbiting our sun, and they represent the closest thing to nearby in the stellar realm. Yet even these stellar neighbors show us light from years and decades past. Sirius, the brightest star in our night sky, blazes at magnitude -1.46 and has captivated humans throughout history. The ancient Egyptians based their calendar on its rising, and it features in mythologies worldwide. But the Sirius we see today is actually Sirius, as it appeared 8.6 years ago. The light hitting your eyes left that stellar system when Barack Obama was president, and the Large Hadron Collider was just beginning its groundbreaking experiments. Sirius is actually a binary star system with a brilliant white main sequence star, Sirius A, orbited by a tiny but incredibly dense white dwarf, Sirius B. The light from this stellar dance has been traveling toward Earth since before the iPhone X was released, carrying information about stellar evolution and the life cycles of massive stars. Vega, the brilliant blue-white star that serves as a calibration standard for stellar magnitude, shows us light from 25 years ago, from a time when the internet was just becoming mainstream, and most people had never heard of something called the World Wide Web. During Vega's light journey to Earth, entire technological revolutions have transformed human civilization. Arcturus, the bright orange giant visible in spring skies, delivers even older news. Its light began the 37-year journey to Earth, when disco was king, and Star Wars was still a new movie. This ancient light comes from a star that's actually moving through our galaxy at high speed, following an orbit that will eventually take it far from our current stellar neighborhood. Polaris, our North Star, and humanity's celestial compass for millennia, shows us light that's approximately 433 years old. When the photons now entering your eyes left Polaris, Galileo was perfecting his telescope, Shakespeare was writing his greatest plays, and the scientific revolution was just beginning. The light from Polaris is older than modern science itself. But distance isn't the only factor that makes these stars remarkable. It's also their diversity. Our local stellar neighborhood is like a cosmic zoo, showcasing the incredible variety of stellar types and evolutionary stages. We have main sequence stars, like our Sun, red giants like Arcturus, nearing the end of their lives, white dwarfs like Sirius B that represent stellar corpses, and red dwarfs like Proxima Centauri that will outlive our Sun by trillions of years. Each of these stellar types evolves on different timescales, meaning the light they're sending us represents different moments in their stellar lives. A red giant might be showing us its death throes from decades ago, while a red dwarf is showing us what could be a virtually unchanged state from centuries past. This temporal diversity creates a fascinating situation. When we look at our local stellar neighborhood, we're not just seeing different places, we're seeing different times and different stages of stellar evolution. The night sky becomes a stellar fossil record, preserving different moments in the lives of different types of stars. The distances to these nearby stars also reveal something crucial about stellar density in our region of the Milky Way. On average, stars in our neighborhood are separated by about 5 light-years. If our galaxy were the size of North America, the average distance between stars would be like the gap between 2 coins placed about 75 kilometers apart. This sparse stellar distribution means that most of the volume of our galaxy, like most of the universe, is empty space. Stars, for all their brilliance and importance, occupy an infinitesimally small fraction of the cosmic volume. We live in a universe that's mostly void, punctuated by tiny islands of matter that we call stars and planets. As we venture beyond our immediate stellar neighborhood, we'll encounter light that's not just decades old, but centuries old, showing us stars as they appeared during the rise and fall of human civilizations. At distances of 100 light-years from Earth, we cross an important threshold. The stars we can see at this distance are showing us light that predates not just individual human lifespans, but entire historical eras. We're beginning to see the universe as it existed before modern human civilization. Consider Deneb, the brilliant supergiant that forms one corner of the Summer Triangle. This massive star, over 200 times the diameter of our Sun, shows us light from approximately 2,600 years ago. When the photons now reaching Earth left Deneb, the Roman Empire didn't exist. The Buddha was still alive, and the ancient Greeks were just beginning to develop democracy. This ancient stellar light connects us to deep human history in a way that's both humbling and awe-inspiring. The light from Deneb has been traveling toward Earth longer than Christianity, Islam, or Buddhism have existed. It began its journey when the Library of Alexandria was being built, and when the Olympic Games were still a new Greek tradition. Rigel, the brilliant blue supergiant in Orion's foot, delivers even more ancient news. Its light started the 860-year journey to Earth during the height of the medieval period, when knights were fighting in the Crusades, and Marco Polo hadn't yet begun his famous journey to China. The photons from Rigel witnessed the rise and fall of entire empires during their cosmic journey. These distant stars also reveal something crucial about stellar lifetimes and evolution. Holg, Sigoneb, and Rigel are both massive supergiants, stars so large and luminous that they burn through their nuclear fuel incredibly quickly. Holg. In cosmic terms, they're living fast and dying young. The light we see from these stars might actually be showing us objects that no longer exist. Deneb, for instance, will eventually explode as a supernova, becoming briefly brighter than entire galaxies before fading to a neutron star or black hole. Because of the light-time delay, this explosion could have already happened, and we might not know about it for thousands of years. We could be seeing the last light from a star that died centuries ago. This introduces one of astronomy's most profound concepts. We're not just seeing the past, we're seeing a past that might no longer exist. The universe we observe is like a vast photographic album, with each page showing a different moment in cosmic history, but with no guarantee that any of those moments still represent reality. At these distances, we also begin to encounter the effects of our galaxy's rotation. The Milky Way spins like a vast pinwheel, with different regions moving at different speeds. Stars 100 light-years away have completed multiple orbits around the galaxy's center since their light began traveling toward us. We're seeing them in completely different locations than where they are now. This revelation that distance creates not just a time delay, but a positional uncertainty, shows us that the universe is even more dynamic and changeable than we might initially realize. Nothing in the cosmos is static, and the further we look, the more we're seeing a universe that no longer exists in the form we observe. As we prepare to expand our view beyond individual stars to the vast stellar cities we call galaxies, we'll discover that these principles of light-time delay and cosmic evolution become even more dramatic. We're about to enter a realm where the light we see is not just historically ancient, it's geologically ancient, older than complex life on Earth itself. Our home galaxy, the Milky Way, represents a tremendous leap in cosmic scale. We're no longer talking about individual stars scattered across dozens of light-years, but about a vast stellar city containing 200 to 400 billion stars spread across 100,000 light-years of space. To understand this scale, we need to grasp that light takes 100,000 years to travel from one edge of our galaxy to the other. When we look toward the galactic center on a clear summer night, we see a bright band of stars stretching across the sky, the combined light of billions of distant suns. But this light represents an average journey time of about 26,000 years. We're seeing the galactic core as it existed when early humans were developing agriculture and the last ice age was ending. The Milky Way's spiral structure, revealed through decades of careful astronomical observation, shows us that our galaxy is organized into grand spiral arms, vast rivers of stars and gas that sweep around the galactic center like the arms of a cosmic pinwheel. These spiral arms are where most of the galaxy's star formation occurs, creating stellar nurseries that birth new suns at a rate of about 1 to 2 per year. Our solar system sits in what's called the Orion arm, or local arm, a minor spiral arm, located about 26,000 light-years from the galactic center, roughly halfway out toward the galactic edge. From our perspective, we're suburban residents of the Milky Way, neither in the dense galactic downtown, nor in the sparse galactic countryside. This position gives us a unique view of our galaxy's structure. When we look toward the constellation Sagittarius in summer, we're looking toward the galactic center, seeing light that began its journey 26,000 years ago. When we look toward Perseus in winter, we're looking toward the outer edge of the galaxy, seeing light from stars that are our galactic neighbors, relatively speaking. But the true scale of the Milky Way becomes clear when we consider its rotation. Our entire solar system orbits the galactic center at a speed of about 220 kilometers per second, roughly 500,000 miles per hour. Even at this tremendous velocity, it takes us approximately 225 million years to complete one orbit around the galaxy's center. The last time Earth was in its current galactic position, dinosaurs had not yet evolved. This galactic year, the time it takes our solar system to orbit the Milky Way once, provides a new way to think about cosmic history. Earth has completed only about 20 galactic years since it formed 4.5 billion years ago. Complex life has existed for less than 3 galactic years. Complex life has existed for less than 3 galactic years. Human civilization represents a tiny fraction of a single galactic year. The light from different parts of our galaxy carries different timestamps, creating a temporal map of stellar evolution. Stars in the galactic center, formed from gas enriched by generations of previous stars, show us light from an era when heavy elements were more abundant than in our region of the galaxy. Stars in the galactic halo, some of the oldest in the Milky Way, show us light from when the galaxy itself was young and metal-poor. This creates a remarkable situation. By studying light from different parts of our own galaxy, we can trace the Milky Way's entire evolutionary history. The outer halo preserves light from the galaxy's youth. The disk shows us middle age, and the central regions reveal the complex chemistry of stellar generations. The Milky Way's magnificent scale also reveals something humbling about our cosmic address. Our entire solar system, from the Sun to the edge of the Oort cloud, would be invisible from the galaxy's center, smaller than a single pixel in even the most detailed galactic photograph. All of human history, every human life that has ever been lived, has occurred within a region of space that represents less than 1/10,000,000th of our galaxy's volume. Yet this vast scale also means incredible diversity. With hundreds of billions of stars, the Milky Way likely contains countless planetary systems, many of which might harbor life. The light traveling between these distant stellar systems could potentially carry information about other living worlds, other civilizations, other forms of consciousness, contemplating their place in the cosmic ocean. As we prepare to venture beyond our galaxy's boundaries, we're about to encounter light that predates not just human history or even complex life, but light that's older than our entire solar system. At the heart of our galaxy lies one of the most extreme environments in the known universe, a supermassive black hole called Sagittarius A*, pronounced Sagittarius A star, surrounded by a dense cluster of ancient stars, exotic objects, and violent processes that generate some of the most energetic phenomena we can observe. The light from this galactic center has been traveling toward us for 26,000 years, a journey that began during Earth's last ice age. Sagittarius A* contains the mass of about 4 million suns compressed into a region smaller than our solar system. While we can't see the black hole itself, by definition, nothing, not even light, can escape once it crosses the event horizon. We can observe the brilliant accretion disk of superheated gas and the violent jets of particles that it produces. This light began its journey to Earth when woolly mammoths roamed the planet and early humans were painting caves in France and Spain. The environment around our galactic center is unlike anywhere else we know. Stars orbit Sagittarius A* at speeds reaching 5,000 kilometers per second, nearly 2% the speed of light. These stars complete their orbits in just a few decades, and their extreme velocities cause relativistic effects that we can actually observe. As these stars swing around the black hole, their light becomes stretched and compressed by gravitational effects and Doppler shifts, providing real-time evidence of Einstein's theories in the most extreme gravitational environment accessible to our telescopes. One star, designated S2, has provided particularly dramatic evidence of these effects. During its closest approach to Sagittarius A** in 2018, astronomers observed both gravitational redshift, the stretching of light waves as they climbed out of the black hole's gravitational well, and relativistic Doppler effects as the star reached 3% of light speed. But remember, we observed this cosmic ballet as it appeared in the year 1992, when the light began its 26,000-year journey to Earth. The galactic center also serves as a laboratory for studying stellar evolution under extreme conditions. The intense gravitational environment and high stellar density create interactions impossible anywhere else in the galaxy. Stars collide and merge, creating exotic objects. Massive stars evolve rapidly in this harsh environment, often ending their lives in spectacular supernovae that add their heavy elements to the galactic center's already rich chemical soup. This region is also a powerhouse of high-energy radiation. The accretion processes around Sagittarius A* generate X-rays, gamma rays, and other forms of electromagnetic radiation across the entire spectrum. However, much of this light is absorbed by the vast dust lanes that lie between us and the galactic center, which is why we can't see it in visible light despite its tremendous energy output. The 26,000-year light travel time to the galactic center creates a profound temporal disconnect. Any dramatic event, a star falling into the black hole, a massive stellar explosion, or a sudden change in the black hole's activity, would remain unknown to us for 26 millennia. The galactic center we observe today actually represents the state of our galaxy's heart during the Paleolithic era, when our ancestors were hunter-gatherers just beginning to develop complex tools and language. This temporal separation becomes even more remarkable when we consider that the entire recorded history of human civilization, about 5,000 years, represents less than 1/5 of the time it takes light to travel from the galactic center to Earth. The fall of Rome, the Renaissance, the Industrial Revolution, both world wars and the space age have all occurred while light from the galactic center has been traveling through just the outermost regions of our galaxy. The ancient light from our galactic center also carries information about the Milky Way's formation and evolution. The stars in this region are among the oldest in our galaxy, formed from primordial gas when the universe was much younger and contained fewer heavy elements. Their spectra reveal the chemical composition of the early universe, showing us what stars were like billions of years ago when galaxies were first forming. Surrounding the central black hole is a nuclear bulge containing billions of older, redder stars. These stellar populations represent different epochs in our galaxy's history, with the oldest stars preserving information about the Milky Way's youth. The light from these ancient stellar populations has been traveling toward us since before our solar system existed, carrying news from an era when the galaxy looked completely different from today. The galactic center also influences the entire galaxy's structure and evolution. The gravitational effects of Sagittarius A* help maintain the galaxy's spiral arms and influence star formation patterns throughout the Milky Way. The energy it produces, while taking 26,000 years to reach us, eventually affects the entire galactic environment. Perhaps most remarkably, the galactic center represents our cosmic downtown, hearth, the gravitational and energetic heart of our stellar city. All the matter in our galaxy, including our solar system, orbits this central region. The light we see from the galactic center is like receiving news from our cosmic capital, but news that's always 26,000 years out of date. As we prepare to look beyond our galaxy's boundaries to the most ancient stellar populations in the Milky Way's halo, all will encounter light that's even older, light from stars that formed when the universe itself was young and dramatically different from the cosmos we observe today. Surrounding our galaxy's disk, like a vast sparse sphere, is the galactic halo, a region populated by the Milky Way's oldest stars, ancient globular clusters, and mysterious dark matter. The light from these stellar fossils has been traveling toward us for times that span the majority of the universe's existence, carrying information about the cosmos when it was young, metal-poor, and dramatically different from today. Globular clusters in our galactic halo are among the oldest objects in the known universe. These tightly packed spheres of stars, containing hundreds of thousands to millions of ancient suns, formed when the universe was only 1 to 2 billion years old. The light from globular clusters like Omega Centauri or M13 in Hercules has been traveling toward Earth for 15,000 to 25,000 years, but the stars themselves are over 12 billion years old, nearly as old as the universe itself. These ancient stellar populations tell a remarkable story preserved in light. When the stars in globular clusters formed, the universe contained almost no heavy elements. The Big Bang had produced only hydrogen, helium, and trace amounts of lithium. All the heavier elements, the carbon in our bodies, the oxygen we breathe, the iron in our blood, had not yet been created by stellar nucleosynthesis. The spectra of these ancient stars, analyzed from their ancient light, reveal this primordial composition. They contain perhaps 1% of the heavy elements found in our sun, making them living fossils from the universe's youth. These stars have been shining continuously since before our galaxy had developed its spiral structure. The halo also contains individual field stars that are even more metal-poor than globular cluster members. Some of these stellar relics contain less than 1,000th of the heavy elements found in our sun, suggesting they formed from gas clouds that had been touched by only a few previous generations of stars. Their light carries information about the very first epochs of star formation in the universe. What makes halo light particularly fascinating is its orbital characteristics. Unlike the stars in our galaxy's disk, which orbit in roughly circular paths in the same direction, halo stars follow highly eccentric, randomly oriented orbits that carry them far above and below the galactic plane. This suggests they formed during chaotic early epochs of galactic assembly, possibly in smaller galaxy fragments that were later absorbed by the growing Milky Way. The light from these halo objects also reveals evidence of our galaxy's cannibalistic past. Astronomers have identified stellar streams, long, thin trails of stars that represent the disrupted remains of smaller galaxies or globular clusters that the Milky Way has torn apart and absorbed. The light from these stellar streams shows us the ongoing process of galactic growth and evolution. Perhaps most remarkably, the halo is where we encounter the universe's first attempts at creating heavy elements. The oldest halo stars show evidence of enrichment by pair instability supernovae, explosions of the very first generation of massive stars which created the first carbon, oxygen, and other elements necessary for planet formation and life. The distances to halo objects, typically 50,000 to 200,000 light-years, mean we're seeing them as they appeared during the late Pleistocene epoch, when early humans were developing art, music, and complex language. But the stars themselves are cosmic time capsules, preserving the conditions and composition of the universe when it was less than 15% of its current age. This creates a profound temporal layering in the light around us. Stars in our galactic neighborhood show us recent stellar evolution. Galactic disk stars reveal intermediate age processes, and halo objects preserve information from the universe's youth. By studying different stellar populations, we're essentially reading the universe's autobiography, written in ancient light. As we prepare to leave our galaxy entirely and venture into the realm of other galaxies, we're about to encounter light that's not just older than our solar system or even our galaxy's disk. We're about to see light from entire galaxy systems as they appeared billions of years ago, when the universe itself was young and still forming its first generation of cosmic structures. The Andromeda Galaxy represents our first glimpse beyond the Milky Way, and with it, we cross into a realm of distances so vast that the light we observe predates not just human civilization, but the evolution of complex life on Earth. At 2.5 million light-years away, Andromeda shows us a massive spiral galaxy, as it appeared when our earliest human ancestors were first diverging from other great apes in Africa. When you look at Andromeda on a dark autumn night, it's visible to the naked eye as a faint oval smudge in the constellation Andromeda. You're seeing light that began its journey across the cosmic void 2.5 million years ago. During the time this light has been traveling toward us, the entire genus Homo evolved. Every human species that has ever lived, Homo habilis, Homo erectus, Neanderthals, Denisovans, and modern humans, has evolved, and in most cases, gone extinct, while this ancient galactic light crossed the emptiness between galaxies. Andromeda, also known as M31, is actually larger than our own Milky Way, containing perhaps 1 trillion stars, compared to our galaxy's estimated 200 milts, 400 billion. Its spiral arms span 220,000 light-years, making it more than twice the diameter of our home galaxy. But from our perspective, this vast stellar city appears as just a small fuzzy patch, a testament to the incredible distances involved in intergalactic space. The light from Andromeda carries information about galactic evolution on unprecedented timescales. When the photons now reaching our telescopes left Andromeda, that galaxy was in a different configuration than it is today. Spiral arms had rotated, stars had been born and died, and the galaxy's supermassive central black hole may have undergone periods of dramatically different activity. We're seeing Andromeda frozen at one moment in its multi-billion-year evolutionary story. Even more remarkable is the fact that Andromeda and the Milky Way are approaching each other at approximately 250,000 miles per hour. In about 4.5 billion years, these two galaxies will collide and merge, creating a new elliptical galaxy that astronomers have nicknamed Milkomeda. However, due to the light-time delay, we won't see the early stages of this cosmic collision until millions of years after they begin. The distance to Andromeda also introduces us to intergalactic space, the vast emptiness between galaxies that makes interstellar space seem crowded by comparison. While the space between stars in our galaxy contains a few atoms per cubic centimeter, intergalactic space contains less than 1 atom per cubic meter. It's a void so empty that it's nearly a perfect vacuum, interrupted only occasionally by thin streams of gas connecting galaxy groups. This emptiness means that the light from Andromeda has traveled through essentially perfect vacuum for 2.5 million years, carrying its galactic information unaltered across the cosmic desert. Unlike light traveling through our galaxy, which can be absorbed or scattered by interstellar dust and gas, intergalactic light arrives at our telescopes, carrying pristine information about its source. Andromeda's ancient light also reveals the galaxy's stellar populations and history. Spectroscopic analysis of this 2.5 million-year-old light shows us that Andromeda contains stars of various ages, from ancient red giants that formed when the universe was young to brilliant blue stars that were created relatively recently. In SIC, the galaxy's spiral arms revealed in this ancient light show active star-forming regions where new suns are being born from vast clouds of gas and dust. The galaxy also hosts numerous satellite galaxies, smaller galactic companions that orbit Andromeda, like cosmic moons. Largest of these, Men-32 and M-110, are visible in telescopes and represent their own island universes, each containing millions to billions of stars. The light from these satellite galaxies has also been traveling for 2.5 million years, showing us an entire galactic family as it appeared in the Pliocene epoch of Earth's history. Perhaps most remarkably, recent observations suggest that Andromeda has been cannibalizing smaller galaxies throughout its history, growing larger by absorbing its neighbors. The light we see from Andromeda may be showing us the aftermath of galactic mergers that occurred millions of years ago, preserved in the ancient photons now reaching our detectors. This introduces a crucial concept for understanding cosmic evolution. Galaxy interactions and mergers are fundamental processes that shape the universe's structure. The light from distant galaxies shows us not isolated objects, but participants in a vast cosmic dance of gravitational attraction, collision, and renewal. As we prepare to explore our local group of galaxies and venture into even deeper space, we'll discover that galactic interactions become increasingly common and dramatic as we look further back in cosmic time. The local group represents our galactic neighborhood, a collection of about 80 galaxies bound together by gravity within a region roughly 10 million light-years across. This cosmic family includes our Milky Way, Andromeda, and dozens of smaller galactic companions, each contributing ancient light that tells the story of how galaxy groups form and evolve over cosmic time. The third largest member of our local group is the Triangulum galaxy M33, located about 3 million light-years away. The light from this spiral galaxy began its journey when early human ancestors like Australopithecus were walking upright in Africa, but had not yet developed stone tools. Triangulum is notable for being one of the most distant objects visible to the naked eye, under exceptionally dark skies, making it a cosmic lighthouse whose ancient beacon has been visible to every generation of humans who have ever looked up at the night sky. Both the Milky Way and Andromeda host families of satellite galaxies, smaller companions that orbit their massive parents like cosmic suburbs. The Milky Way's most famous satellites are the Large and Small Magellanic Clouds, visible from the southern hemisphere as fuzzy patches that look like detached pieces of the Milky Way. Their light reaches us from distances of about 160,000 and 200,000 light-years respectively, showing us these galaxies as they appeared during the Middle Pleistocene, when early humans were mastering fire and developing complex hunting strategies. These satellite galaxies are particularly interesting because they're close enough that we can study individual stars within them, yet far enough that their light carries significant temporal information. The Magellanic Clouds are currently being disrupted by the Milky Way's gravitational pull, creating the Magellanic Stream, a trail of gas and stars stretched across the southern sky. The light from this ongoing galactic interaction shows us gravitational processes that have been unfolding for hundreds of thousands of years. Andromeda's satellite system includes MM32 and M110, along with numerous smaller dwarf galaxies. The light from these companions, traveling for 2.5 million years, shows us a galactic family in various stages of evolution. Some satellites are actively star-forming, their light revealing young blue stellar populations, while others are dominated by ancient red stars that formed when the universe was much younger. The local group structure also reveals evidence of dark matter's influence on cosmic evolution. The distribution and motion of galaxies within our group can only be explained if they're embedded in halos of invisible dark matter that outmass the visible stars by factors of 10 or more. The ancient light from local group galaxies carries information about how these dark matter structures have grown and interacted over millions of years. One of the most remarkable aspects of local group light is that it shows us galactic archaeology in action. Many of the smaller galaxies bear the scars of ancient interactions, distorted shapes, stellar streams, and unusual velocity patterns that reveal close encounters with larger galaxies. The light from these disrupted systems preserves evidence of gravitational encounters that occurred when the light began its journey millions of years ago. The local group also provides our first clear view of cosmic expansion. While the galaxies within our group are bound together by gravity and will remain associated indefinitely, the space around our group is expanding, carrying more distant galaxy groups away from us. The light from local group galaxies shows us objects that are gravitationally connected to us, representing the largest scale on which gravity can overcome cosmic expansion. As we study the ancient light from our galactic neighborhood, we're seeing the local group as it existed when complex life was just beginning to emerge on Earth. The galactic interactions, star formation processes, and evolutionary changes preserved in this light show us how galaxy groups develop and mature over cosmic time. This local group light also represents a boundary in our cosmic journey. Beyond about 10 million light-years, we'll encounter galaxies that are no longer gravitationally bound to us, galaxies whose light shows them receding due to cosmic expansion. We're about to leave our cosmic home and venture into the expanding universe beyond. As we venture beyond the local group's 10 million light-year boundary, we encounter a fundamentally different cosmic realm. Here, the ancient light shows us galaxies that are no longer gravitationally bound to our local family, galaxies that are receding from us due to the expansion of space itself. We're entering the domain where Hubble's law, the relationship between distance and recession velocity, begins to dominate our observations. The Virgo cluster, our nearest major galaxy cluster, lies approximately 54 million light-years away. The light from this vast collection of over 1,300 galaxies began its journey toward us during the Eocene epoch, when Earth was a dramatically different world. There were no ice caps at the poles, the climate was tropical from pole to pole, and the first ancestors of horses, whales, and primates were just beginning to evolve. During the 54 million years that Virgo's light has been traveling toward us, India collided with Asia to form the Himalayas, and the entire evolutionary lineage leading to modern mammals diversified and flourished. The Virgo cluster represents our first encounter with truly massive cosmic structures. This gravitationally bound collection of galaxies spans about 15 million light-years and contains a total mass equivalent to 1.2 million billion suns. At its heart lies Mylliae 87, a massive elliptical galaxy that hosts one of the largest known supermassive black holes, the same black hole that made headlines in 2019 when the Event Horizon Telescope captured its first direct image. But here's the remarkable thing. That famous black hole image shows M87's central region. As it appeared 54 million years ago, the jets of plasma streaming from this black hole at nearly the speed of light, the accretion disk glowing at billions of degrees, the gravitational lensing effects around the event horizon. All of this cosmic violence was happening when our mammalian ancestors were small, furry creatures scurrying through Eocene forests. The light from Virgo cluster galaxies also reveals the effects of cosmic expansion for the first time in our journey. These galaxies are moving away from us at approximately 1,200 kilometers per second, not because they're physically moving through space, but because the space between us and them is expanding. This introduces a crucial concept. At these distances, we must distinguish between the light travel time, 54 million years, and the current distance to these objects, which is greater due to cosmic expansion. Moving further out, we encounter the Coma cluster at about 320 million light-years distance. The light from this massive galaxy cluster began its journey during the Carboniferous period, when Earth's continents were still assembling into the supercontinent Pangaea. The coal deposits that powered the Industrial Revolution were being formed by vast swamp forests when Coma's light began its journey to our telescopes. The Coma cluster contains over 1,000 known galaxies and served as one of the key observations that led to the discovery of dark matter. In the 1930s, astronomer Fritz Zwicky noticed that the galaxies in Coma were moving too fast for the cluster's visible mass to hold them together gravitationally. The ancient light from Coma was providing evidence for invisible matter that astronomers wouldn't fully understand for decades. At these distances, we begin to see cosmic evolution in action. The galaxies in these distant clusters appear different from nearby galaxies. They contain higher proportions of elliptical galaxies and show evidence of more frequent galactic mergers. The ancient light preserves a time when the universe was denser, more violent, and more active in its galaxy-building processes. The Perseus cluster, at about 240 million light-years away, shows us light from the Permian period, the era just before the greatest mass extinction in Earth's history. When this light began its journey, the ancestors of mammals and dinosaurs were just diverging, and life on Earth was about to face its greatest challenge. The galaxies in Perseus appear to us frozen at this moment in both cosmic and terrestrial history. These distant galaxy clusters also reveal the large-scale structure of the universe. They're not randomly distributed, but form part of a vast cosmic web, filaments of matter separated by enormous voids. The Virgo cluster, Coma cluster, and Perseus cluster are all part of massive structure formations that span hundreds of millions of light years. The light from these clusters shows us the universe's architecture as it existed hundreds of millions of years ago. Perhaps most remarkably, at these distances, we begin to see the universe's expansion history preserved in light. Each galaxy cluster we observe represents a different epoch in cosmic evolution. More distant clusters, showing us the universe when it was younger, denser, more rapidly. The recession velocities of these clusters, measured from their ancient light, provided the first evidence for cosmic acceleration, the discovery that the universe's expansion is speeding up due to dark energy. The ancient light from these distant galaxy clusters also carries information about the cosmic microwave background radiation that fills the universe. As this primordial light passes through galaxy clusters, it gets slightly distorted by the cluster's gravity and hot gas, creating what astronomers call the Sunyaev-Veldovich effect. This allows us to study both the ancient light from the cosmic microwave background and the more recent light from galaxy clusters simultaneously. As we venture even deeper into space and time, approaching distances of billions of light years, we'll encounter light that's not just geologically ancient. It's light from when the universe itself was fundamentally different, showing us cosmic epochs, when stars and galaxies were first forming, and the universe was beginning to transition from its dark age to the light-filled cosmos we observe today. At distances approaching hundreds of millions of light years, we encounter a profound intersection of cosmic and terrestrial history. The ancient light, reaching us from distant galaxy clusters and individual galaxies, carries information from epochs when Earth itself was a dramatically different world. When dinosaurs ruled the planet, continents had different configurations, and the very chemistry of our atmosphere was unlike today's. Consider the light from galaxies in the Hydra cluster, located approximately 190 million light-years away. When the photons now entering our telescopes began their cosmic journey, Earth was in the midst of the Jurassic period. Massive sauropods like Diplodocus and Brontosaurus were grazing in lush forests. The first birds were evolving from feathered dinosaurs, and the supercontinent Pangaea was beginning to break apart. The Atlantic Ocean was just a narrow rift between North America and Europe, and what would become the Mediterranean Sea was still the ancient Tethys Ocean. This creates an extraordinary temporal connection. The same cosmic processes that were forming stars and sculpting galaxies 190 million years ago were also setting the stage for one of the most successful evolutionary experiments in Earth's history. While massive elliptical galaxies in the Hydra cluster were cannibalizing smaller companions in gravitational dances lasting millions of years, on Earth, natural selection was fine-tuning the biological machines that would dominate terrestrial ecosystems for over 150 million years. The light from these distant galaxies shows us cosmic evolution during what astronomers call the recent universe, a time when galaxy formation had largely completed its most violent phase. But galactic interactions and stellar evolution continued to reshape cosmic structures. Many of the galaxies we observe at these distances appear more active than their nearby counterparts, with higher rates of star formation and more prominent active galactic nuclei powered by feeding supermassive black holes. Moving deeper into space, we encounter the Hercules cluster at about 500 million light-years distance. The light from this massive collection of galaxies began its journey during Earth's Ordovician period, when life was still confined to the oceans, and the largest organisms were primitive marine invertebrates. There were no plants on land, no forests, no complex ecosystems, just barren continents surrounding seas teeming with trilobites, early fish, and marine invertebrates that would seem alien to modern eyes. During the 500 million years that this galactic light has been traveling toward us, life on Earth underwent some of its most dramatic transformations. The first plants colonized land, forests spread across the continents, animals followed plants onto dry land, and the entire terrestrial biosphere evolved from scratch. Fish developed into amphibians. Amphibians gave rise to reptiles. Reptiles evolved into both mammals and dinosaurs. Dinosaurs ruled for 165 million years, and then mammals inherited the Earth after the Great Extinction, 66 million years ago. Yet, from the perspective of cosmic evolution, 500 million years represents a relatively brief moment. The galaxies in the Hercules cluster appear remarkably similar to nearby galaxies, suggesting that the fundamental processes of galactic evolution, stellar birth and death, supermassive black hole growth, and large-scale structure formation operate on timescales much longer than terrestrial biological evolution. This temporal comparison reveals something profound about the relationship between cosmic and biological time. While life on Earth has undergone multiple complete reinventions during the time it takes light to travel from distant galaxy clusters, the galaxies themselves appear to evolve much more slowly. Stellar populations change gradually, galactic morphology shifts over billions of years, and even dramatic events like galactic mergers unfold over hundreds of millions of years. The light from these dinosaur-era galaxies also carries information about cosmic chemical evolution. By this point in cosmic history, 500 to 200 million years ago, in look-back time, successive generations of stars had already enriched the universe with heavy elements. The spectra of these ancient galaxies show evidence of carbon, oxygen, silicon, and iron produced by stellar nucleosynthesis, elements that were being incorporated into new generations of stars and planetary systems throughout the universe. Some of these distant galaxies were likely forming planetary systems during Earth's Mesozoic era, creating worlds that might have developed their own versions of complex life while dinosaurs roamed our planet. The light we observe from these galaxies might be illuminating alien worlds where evolution was conducting its own experiments with complexity, intelligence, and consciousness. The recession velocities of these distant galaxies, measured from their ancient light, also provide crucial information about cosmic expansion during Earth's geological past. The universe was expanding more slowly 200 to 500 million years ago than it is today, before dark energy became the dominant component driving cosmic acceleration. These galaxies preserve information about the transition period when matter and dark energy were becoming equal in density. Perhaps most remarkably, the light from these distant galaxies connects cosmic and terrestrial evolution in ways that challenge our perspective on time itself. While paleontologists study dinosaur fossils preserved in rock layers to understand life 100 million years ago, astronomers study galactic light to understand cosmic evolution during the same epoch. Both are forms of time travel, both preserve information about the past, and both reveal that the universe, whether biological or cosmic, has been in constant change throughout its history. As we prepare to venture even deeper into space and time, approaching the billion-light-year mark, we'll encounter light from epochs before complex life existed on Earth, when our planet was inhabited only by single-celled organisms, and the universe itself was entering a crucial phase of cosmic evolution. At distances approaching 1 billion light-years, we encounter light that predates not just complex life on Earth, but most of the oxygen in our atmosphere. These ancient photons began their journey when our planet was inhabited primarily by single-celled organisms. The great oxygenation event that transformed Earth's atmosphere was still a relatively recent development in terrestrial history. Galaxies at these distances, such as those in the distant Abell galaxy clusters, show us light from approximately 1 billion years ago, a time when Earth's continents were barren, rock and primitive oceans hosted only the earliest forms of multicellular life. The most complex organisms were simple algae and bacteria. There were no plants, no animals, no complex ecosystems. Earth's atmosphere contained only a fraction of today's oxygen levels, and the planet would have been completely uninhabitable for any modern form of complex life. Yet during this same epoch, the galaxies we observe were already mature stellar cities. Many contained populations of stars that were themselves already billions of years old, formed during the universe's youth, when cosmic evolution was proceeding much more rapidly than biological evolution on any individual world. This reveals a fundamental asymmetry between cosmic and biological timescales. While life on Earth was still experimenting with the most basic forms of cellular organization, the universe had already constructed massive, complex galactic structures. The light from these billion-year distant galaxies also shows us the cosmic web in an earlier configuration. The large-scale structure of the universe, the vast filaments of matter, separated by enormous voids, appears denser and more connected at these distances. The light from these billion-year distant galaxies also shows us the cosmic web in an earlier configuration. The large-scale structure of the universe, the distant Kalv Indri Polar, so being Siven Universe. Galaxy clusters were more compact, galactic interactions were more frequent, and the overall rate of star formation throughout the universe was higher than it is today. This billion-year-old light carries signatures of cosmic evolution that we can't observe in the nearby universe. Many of these distant galaxies appear bluer than their modern counterparts, indicating higher rates of star formation and younger stellar populations. The supermassive black holes at galactic centers were more active, creating brilliant quasars and active galactic nuclei that outshone entire galaxies. The universe was in many ways more energetic and violent than the relatively quiet cosmos we observe nearby. Spectroscopic analysis of this ancient light reveals the chemical composition of the universe 1 billion years ago. While the overall abundance of heavy elements was lower than today, successive generations of stellar death had already enriched the cosmic gas supply with carbon, oxygen, silicon, and iron. Planetary systems forming during this epoch would have had access to the chemical ingredients necessary for rocky planet formation and potentially even biological evolution. This raises a profound question. While Earth was still inhabited only by primitive life forms, were there other worlds in these distant galaxies that had already developed complex life, intelligence, or even technological civilizations? The light we observe from billion-year distant galaxies might be illuminating alien worlds where evolution had a billion-year head start on terrestrial development. Discreditability. The recession velocities of these distant galaxies, preserved in their billion-year-old light, provide crucial information about the history of cosmic expansion. During the epoch when this light began its journey, dark matter was still the dominant component of the universe's energy density, and cosmic expansion was decelerating due to gravitational attraction between matter. The transition to dark energy dominance and accelerating expansion would not occur for several billion more years. These billion-year-old photons also carry information about galaxy formation processes that we can no longer observe in the nearby universe. Many of these distant galaxies show evidence of ongoing major mergers, collisions between massive galaxies that trigger intense bursts of star formation and feed central supermassive black holes. The nearby universe is relatively quiet, with most major galactic mergers having occurred in the distant past, but this ancient light preserves the violent epoch of galaxy assembly. The vast distances involved, typically 8 to 12 billion trillion kilometers, mean that these photons have traveled through cosmic expansion for their entire journey. The galaxies that emitted this light are now much farther away than they were when the light began its journey, carried by the expansion of space itself to distances that approach the observable universe's edge. Perhaps most remarkably, these billion-year-old photons represent a form of cosmic archaeology that rivals any terrestrial excavation. While paleontologists dig through rock layers to study life forms from hundreds of millions of years ago, astronomers collect ancient light to study galactic evolution from billions of years ago. Both are uncovering the deep history of change and development, whether biological or cosmic. As we venture even deeper into space and time, approaching the limits of what our most powerful telescopes can observe, we'll encounter light that predates not just complex life on Earth, but the formation of our solar system itself. As we push toward the limits of what our most powerful telescopes can detect, we approach distances of 10 to 13 billion light-years, the edge of the observable universe. Here, we encounter light that began its journey when the cosmos itself was young, violent, and dramatically different from the universe we observe today. This ancient light shows us epochs before our solar system existed, before the Milky Way had developed its spiral structure, and before the universe had settled into its current configuration. At these extreme distances, we observe galaxies as they appeared when the universe was only 1 to 3 billion years old, less than 25% of its current age. These early galaxies appear fundamentally different from their modern descendants. They're typically smaller, more irregular in shape, and undergoing much more rapid star formation. Many are caught in the act of violent mergers, gravitational interactions that trigger explosive bursts of stellar birth at rates hundreds of times higher than we observe in today's galaxies. Perception is fire into be sieve in today's galaxies. The light from these primordial galaxies also reveals the universe's transition from its dark age to the epoch of reionization. During the universe's first few 100 million years, space was filled with neutral hydrogen that absorbed most visible light. The first stars and galaxies had to ionize this cosmic fog before their light could travel freely through space. The most distant galaxies we can observe represent the cosmic lighthouses that ended the universe's dark age and made the transparent cosmos possible. These ancient galaxies show us star formation under conditions that no longer exist anywhere in the universe. The gas from which their stars formed contained almost no heavy elements, less than 1% of the metal content found in our Sun. This means the first generations of stars were fundamentally different from modern stars, likely more massive, hotter, and shorter lived. When these population 3 stars died in spectacular supernovae, they created the first heavy elements and began the cosmic chemical evolution that would eventually make planets and life possible. The supermassive black holes at the centers of these early galaxies present a major puzzle for astronomers. Some of these ancient galaxies host black holes containing billions of solar masses, yet they formed when the universe was less than 1 billion years old. Understanding how such massive black holes could grow so quickly in the early universe remains one of astronomy's greatest challenges. The distances to these primordial galaxies are so vast that cosmic expansion becomes a major factor in interpreting their light. Due to the expansion of space, during the billions of years, their light has traveled toward us. These galaxies are now much farther away than the distance light could travel in the age of the universe. Some of the galaxies whose light we observe from 13 billion years ago are now over 30 billion light-years away, carried to these distances by cosmic expansion itself. At these extreme distances, we also begin to encounter the cosmic microwave background radiation, the afterglow of the Big Bang itself. This primordial light, emitted when the universe became transparent for the first time, represents the oldest light in the universe and the most distant objects we can observe. Beyond this cosmic horizon, the universe becomes opaque to electromagnetic radiation, limiting how far back in time we can see. The most distant galaxies observable today, detected by the Hubble Space Telescope and the recently launched James Webb Space Telescope, show us light from when the universe was only 400 to 600 million years old. These galactic ancestors appear as tiny red-shifted smudges that require the most sophisticated instruments humanity has ever built to detect and study. Yet even these incredibly distant observations represent only a fraction of the universe's true extent. The observable universe, the sphere of space from which light has had time to reach us, represents only the portion of cosmos we can study through electromagnetic radiation. The actual universe likely extends far beyond what we can observe, possibly infinitely in all directions. As we approach the ultimate boundary of observable space and time, we're about to encounter the most ancient light of all, the cosmic microwave background radiation that carries information from the universe's birth itself. At the very edge of the observable universe lies the most ancient light that can ever be detected, the cosmic microwave background radiation. This primordial glow represents the universe's baby picture, showing us the cosmos as it appeared just 380,000 years after the Big Bang, when the entire universe underwent a dramatic transformation from opaque to transparent for the first time in its history. To understand this ancient light, we must journey back to an epoch when the universe was radically different from today. In its first 380,000 years, the cosmos was a hot, dense plasma where temperatures exceeded 3000 Kelvin throughout all of space. At these extreme temperatures, electrons couldn't bind to atomic nuclei Any atom that tried to form was immediately torn apart by the universe's intense thermal energy. Tuones, the cosmos was filled with a soup of free electrons, protons and photons, with light constantly scattering off the unbound electrons, like headlights trying to penetrate thick fog. This early universe was literally opaque. Light could travel only tiny distances before colliding with a free electron and scattering in a new direction. Photons were trapped in an endless dance of absorption and re-emission, unable to travel freely through space. The universe was dark, not because there was no light, but because light couldn't escape the cosmic fog of free electrons. Then, as cosmic expansion continued to cool the universe, something remarkable happened. When the temperature dropped to about 3000 Kelvin, roughly half the temperature of the sun's surface, electrons finally had little enough energy to bind with protons and form the first neutral hydrogen atoms. This moment, called recombination, transformed the universe in an instant from an opaque plasma to a transparent gas. For the first time in cosmic history, light could travel freely across space. The photons that had been trapped in the primordial plasma were suddenly released, flooding the universe with the afterglow of creation itself. This moment, occurring simultaneously throughout the observable universe, created what we now observe as the cosmic microwave background radiation. But here's the remarkable thing. We can still see this ancient light today. The same photons that were released when the universe first became transparent are still traveling through space, carrying pristine information about cosmic conditions. 380,000 years after the Big Bang, these photons have been journeying through the expanding universe for 13.8 billion years, and they're arriving at our detectors right now. However, cosmic expansion has dramatically altered these ancient photons during their journey. When they were first emitted, they had wavelengths corresponding to visible and infrared light. The universe literally glowed like the surface of a cool star. But 13.8 billion years of cosmic expansion has stretched their wavelengths by a factor of about 1,100, shifting them from visible light into the microwave portion of the electromagnetic spectrum. This is why we call it the cosmic microwave background. The ancient light of creation, red-shifted by cosmic expansion, now appears as microwave radiation with a temperature of just 2.7 Kelvin above absolute zero. This radiation fills the entire universe uniformly, coming from every direction in space with nearly identical intensity. The cosmic microwave background represents the ultimate limit of how far back in time we can see using electromagnetic radiation. Before recombination, the universe was opaque to light, so no photons from earlier epochs can reach our telescopes. This primordial radiation is literally the oldest light in the universe, the first light that could travel freely through space. Detailed observations of the cosmic microwave background, particularly by satellites like COBE, MIMAP, and Planck, have revealed incredibly subtle variations in temperature across the sky, differences of just a few millionths of a degree. These tiny fluctuations represent density variations in the primordial plasma that would eventually grow, through gravitational attraction, into the cosmic web of galaxies, clusters, and voids we observe today. The cosmic microwave background is remarkably uniform, varying by less than 0.001% across the entire sky. This extraordinary uniformity tells us that the early universe was incredibly smooth and homogeneous, with only tiny quantum fluctuations that would later seed the formation of all cosmic structure. The fact that regions of the sky separated by vast distances show nearly identical temperatures suggests that they were once in causal contact, a puzzle that led to the theory of cosmic inflation. Perhaps most remarkably, the cosmic microwave background provides a direct view of the universe when it was only 0.003% of its current age, while the most distant galaxies show us the cosmos when it was perhaps 5% of its current age. The cosmic microwave background takes us back to when the universe was still an infant, showing us the moment when the cosmos first became recognizable as the transparent, light-filled universe we inhabit today. This ancient light also carries information about the universe's fundamental properties, its geometry, composition, and age, encoded in the precise pattern of temperature fluctuations across the sky. The photons of the cosmic microwave background have been traveling through space for 13.8 billion years, longer than our solar system has existed, longer than complex life has inhabited Earth, and nearly as long as the universe itself has existed. These ancient messengers carry the oldest information accessible to human observation, having journeyed across the entire history of cosmic evolution to reach our detectors today. When these photons began their journey, the universe was a fundamentally alien place. There were no stars, no galaxies, no planets, no complex atoms beyond hydrogen and helium. The cosmos consisted entirely of a cooling gas of primordial elements in perfect darkness, just beginning to respond to the tiny gravitational seeds that would eventually grow into the cosmic web. The temperature everywhere in space was about 3,000 Kelvin, hot enough to glow like a giant ember, filling all of space. During the 13.8 billion years that cosmic microwave background photons have been traveling toward us, the universe has undergone complete transformation. The first stars ignited when the universe was about 100 million years old, ending the cosmic dark age and beginning the process of stellar nucleosynthesis that would create the heavy elements necessary for planets and life. These photons were already 100 million years into their journey when the first light from the first stars began to shine. By the time these ancient photons had traveled for 500 million years, the first galaxies were forming from gravitational collapse of dark matter halos. Massive black holes were growing at galactic centers, and the first generation of stellar death was beginning to enrich the universe with carbon, oxygen, and other heavy elements. The cosmic microwave background photons witnessed this entire epoch of early galaxy formation during their journey, though they passed through these evolving structures essentially undisturbed. When the photons had been traveling for about 4 billion years, something remarkable happened in the local universe, or a gravitational collapse in a region that would become our local galaxy group, led to the formation of the Milky Way. During the following billions of years of their journey, these ancient photons watched our galaxy take shape, develop spiral arms, and begin the process of stellar evolution that would eventually lead to the formation of our solar system. About 9.2 billion years into their journey, roughly 4.6 billion years ago, something extraordinary occurred in an unremarkable region of the Milky Way's Orion arm. A cloud of gas and dust, enriched by generations of stellar death, began to collapse under its own gravity. The cosmic microwave background photons were passing through our local region of space during the exact epoch when our solar nebula was condensing, when the sun was igniting, and when the planets were forming through accretion in the protoplanetary disk. These photons continued their journey as Earth underwent its most dramatic transformations. They were traveling through intergalactic space when the first life appeared in terrestrial oceans, when oxygen began accumulating in our atmosphere, when complex cells evolved, and when multicellular life first emerged. The entire history of life on Earth, from its earliest single-celled origins to the development of intelligence and consciousness, has occurred during the final portion of these photons' cosmic journey. The remarkable thing about cosmic microwave background photons is their pristine preservation of ancient information. Unlike light from distant galaxies, which can be absorbed or scattered by intervening matter, these primordial photons have traveled through nearly empty space for their entire journey. The intergalactic medium they've traversed is so sparse, less than 1 atom per cubic meter, that most photons complete their 13.8 billion year journey without interacting with a single particle of matter. However, the photons haven't been completely unaffected by their journey. Cosmic expansion has continuously stretched their wavelengths, cooling them from the temperature of a glowing coal to just 2.7 degrees above absolute zero. This expansion has been going on for every moment of their journey, gradually redshifting the light from visible wavelengths into the microwave region of the spectrum. The cosmic microwave background also provides a unique form of cosmic archaeology. By studying the tiny temperature variations in this radiation, astronomers can map the density fluctuations that existed in the primordial universe. These fluctuations represent the gravitational seeds that would eventually grow into galaxies, clusters, and the large-scale structure we observe today. In essence, the cosmic microwave background shows us a map of the universe's destiny written in its earliest moments. Perhaps most remarkably, every cubic centimeter of space around us contains about 400 cosmic microwave background photons right now. You are literally surrounded by the light of creation. Photons that have been traveling since the universe became transparent are passing through your body at this very moment. These ancient messengers carry information about cosmic conditions that existed before stars, before galaxies, before any of the complex structures that define the modern universe. The detection and study of the cosmic microwave background represents one of humanity's greatest scientific achievements. We have learned to capture and analyze light that predates the formation of our entire cosmic neighborhood, extracting from it information about the universe's age, composition, geometry, and ultimate fate. These 13.8 billion-year-old photons have become our most reliable witnesses to the conditions that existed in the infant universe. Yet even these ancient photons have a limitation. They can only show us the universe from the moment it became transparent onward. The first 380,000 years of cosmic history remain hidden behind the opaque veil of the primordial plasma, accessible only through theoretical physics, and the traces left in the cosmic microwave background's subtle patterns. As we consider what lies beyond this ultimate observational horizon, we encounter the deepest questions about the nature of space, time, and the cosmos itself. Holem Sov, when experience our gavers. The cosmic microwave background represents an absolute boundary, the furthest back in time we can see using light of any wavelength. Beyond this ancient glow lies a realm hidden from direct observation, the first 380,000 years of cosmic history, when the universe was opaque to electromagnetic radiation. This hidden epoch contains the deepest mysteries of existence, the moment of cosmic birth, the origin of space and time, and the fundamental forces that shaped reality itself. Before the universe became transparent, cosmic history unfolds like a story written in physics rather than light. The cosmic microwave background shows us the universe at 380,000 years old, but theoretical physics and particle accelerator experiments allow us to trace cosmic evolution back much further. As we work backward in time, the universe becomes progressively hotter, denser, and more extreme. At 1 second after the Big Bang, the entire universe had a temperature of about 10 billion Kelvin, roughly 1,000 times hotter than the Sun's core. At this moment, the cosmic soup consisted of protons, neutrons, electrons, and photons in thermal equilibrium. Nuclear fusion was occurring throughout all of space, creating the primordial helium that we still observe in the universe today. This era of Big Bang nucleosynthesis lasted only about 20 minutes, but it determined the cosmic abundance of light elements for all subsequent history. Going back even further, to just 1 millisecond after the Big Bang, protons and neutrons themselves didn't exist. The universe was so hot and dense that only quarks, the fundamental building blocks of protons and neutrons, could exist as free particles. This quark epoch represents a state of matter so extreme that we can only recreate tiny samples of it in our most powerful particle accelerators for fractions of a second. As we approach the Planck time, 10 circumflex 43 seconds after the Big Bang, we reach the absolute limit of our physical theories. At this moment, the universe was so small, hot, and dense that quantum effects became important on cosmic scales. Space and time themselves may have been discrete rather than continuous, and our normal concepts of causality and physical law may not have applied. This is the realm where Einstein's general relativity breaks down, and where a theory of quantum gravity, still undeveloped, would be necessary to understand cosmic evolution. What lies beyond the Planck time remains pure speculation. Some theories suggest that the Big Bang was not a beginning, but a transition, perhaps a bounce from a previous contracting universe, or an emergence from a higher dimensional space, or even a quantum fluctuation in an eternal multiverse. These ideas push the boundaries of science into philosophy, raising questions about whether the universe had a beginning or has always existed in some form. The hidden epoch before the cosmic microwave background also contains the inflationary period, a proposed era of exponential cosmic expansion that occurred in the universe's first fraction of a second. If inflation really happened, it would explain many puzzling features of the cosmic microwave background, including its remarkable uniformity and the precise pattern of density fluctuations that seeded galaxy formation. Inflation theory makes a startling prediction. The observable universe represents only a tiny fraction of the total cosmos. If inflation is correct, the actual universe extends far beyond what we can observe, possibly infinitely, in all directions. Our observable universe, everything within 13.8 billion light-years, would be like a small bubble in an infinite sea of space and time. This raises profound questions about cosmic uniqueness and repetition. In an infinite universe, the exact pattern of matter and energy that created our cosmic neighborhood might repeat countless times, leading to the possibility of identical copies of galaxies, solar systems, and even individual observers scattered throughout the vast expanse beyond our observational horizon. The boundary represented by the cosmic microwave background also reminds us that astronomy is ultimately limited by the speed of light and the finite age of the universe. We can never observe the universe's beginning directly. We can only extrapolate backward using physics and mathematics. The cosmic microwave background represents the oldest possible photograph of the cosmos, but the universe's birth certificate remains hidden beyond the opaque veil of the primordial plasma. Yet this limitation doesn't diminish the remarkable achievement of observing 13.8-billion-year-old light. We have learned to read the universe's autobiography, written in ancient photons, extracting from the cosmic microwave background a detailed understanding of cosmic composition, age, and destiny. One of the most mind-bending revelations of modern cosmology is that the universe's immense scale isn't static. Space itself is expanding, carrying galaxies away from each other like raisins in rising bread dough. This cosmic expansion means that the most distant objects we observe are not only incredibly far away, but they're also much farther away now than they were when their ancient light began its journey to us. Understanding this expansion is crucial to grasping why 13.8-billion-year-old light reveals a universe unimaginably larger than we might initially expect. The expansion of space is not like any motion we experience in everyday life. Galaxies aren't flying through space away from each other. Instead, the space between them is literally growing, creating new distance where none existed before. This means that very distant galaxies can be receding from us faster than the speed of light without violating Einstein's cosmic speed limit, because they're not moving through space, but being carried by expanding space itself. Consider the cosmic microwave background, that 13.8-billion-year-old afterglow of the Big Bang. When those photons were emitted, the regions of space that produced them were only about 42 million light-years away from where our Milky Way would eventually form. But during the 13.8 billion years that this light has been traveling toward us, cosmic expansion has carried those same regions of space to distances of approximately 46.5 billion light-years away. This creates a profound conceptual challenge. How can we observe objects that are now 46.5 billion light-years away if the universe is only 13.8 billion years old and light travels at a fixed speed? The answer lies in understanding that the photons have been traveling through expanding space. Like a runner on a moving walkway, the light makes progress toward us while the space through which it travels continuously expands. The expansion rate, quantified by the Hubble constant, means that space grows by about 70 kilometers per second for every megaparsec of distance, roughly 23 kilometers per second for every million light-years. This seems slow on human scales, but it becomes dramatic across cosmic distances. Two galaxies separated by 1 billion light-years are receding from each other at about 23,000 kilometers per second due to expansion alone, nearly 8% of light speed. This expansion affects the ancient light we observe in measurable ways. The wavelengths of photons get stretched as they travel through expanding space, shifting them toward the red end of the spectrum, what astronomers call cosmological redshift. The cosmic microwave background, originally emitted as visible and near-infrared light, has been redshifted by a factor of about 1,100, transforming it into microwave radiation. This redshift serves as a cosmic timestamp, telling us how much the universe has expanded since the light was emitted. For the most distant galaxies, observable by the Hubble Space Telescope, redshift measurements indicate that the universe was only 5 to 10% of its current size when their light was emitted. These galaxies appear compressed and distorted compared to nearby galaxies, not because of observational effects, but because cosmic expansion has literally stretched the universe by a factor of 10⁻20 during their light's journey to us. The expansion of space also creates a cosmic horizon, a boundary beyond which we cannot observe objects, not because their light hasn't had time to reach us, but because they're receding faster than light due to expansion. This horizon is constantly growing as light from more distant regions reaches us, but it also means that there are parts of the universe we will never be able to observe, no matter how long we wait or how powerful our telescopes become. Perhaps most remarkably, cosmic expansion means that the universe we observe is like a vast archaeological site where different distances correspond to different epochs in cosmic history. When we look at objects 1 billion light-years away, we see the universe when it was 90% of its current age. Objects 5 billion light-years away show us the cosmos at 64% of its current age. The most distant observable galaxies, at 13+ billion light-years, reveal the universe when it was less than 10% of its current age. This creates a situation unique in all of science. We can directly observe the past of the system we're studying. Geologists must dig through rock layers to study Earth's history. Paleontologists must search for fossil remains to understand ancient life. But astronomers can directly observe cosmic evolution by looking deeper into space. The expanding universe preserves its own history in the form of ancient light, traveling toward us across the growing cosmic distances. The expansion also reveals that our observable universe, everything within about 46.5 billion light-years, represents only a tiny fraction of the total cosmos. If cosmic inflation is correct, the actual universe extends far beyond our observational horizon, possibly infinitely in all directions. Our entire observable universe might be like a single atom in an ocean of unobservable space and time. But cosmic expansion isn't slowing down as we might expect from a universe where gravity should be pulling everything together. Observations of distant supernovae in the 1990s revealed that expansion is actually accelerating, driven by a mysterious component called dark energy that comprises about 68% of the universe's total energy density. This means that distant galaxies are not only receding from us due to expansion, but their recession is speeding up over time. This acceleration has profound implications for the universe's future. Galaxies that are currently observable will eventually disappear beyond our cosmic horizon as acceleration carries them away faster than light. In the far future, observers in our local group will see a universe that appears empty except for the galaxies gravitationally bound to us, a cosmic isolation that will make the universe's expansion invisible to future astronomers. The expanding universe also means that the ancient light around us represents a one-time gift from the cosmos. Each ancient photon that reaches our telescopes has been traveling for billions of years and will never pass our way again. One of the most puzzling aspects of the cosmic microwave background, and a key clue to understanding the early universe, is its extraordinary uniformity. This ancient light shows essentially the same temperature in all directions across the sky, differing by less than 0.001% between regions separated by vast distances. This uniformity creates what cosmologists call the horizon problem, a puzzle that challenges our understanding of how information and energy can be shared across cosmic distances. To understand this problem, consider two regions of the cosmic microwave background on opposite sides of the sky. separated by an angle of 180 degrees as seen from Earth. The light from these regions began its journey 13.8 billion years ago when the universe became transparent. At that time, these regions were separated by about 84 million light-years, but they showed virtually identical temperatures. Here's the puzzle. If these regions were 84 million light-years apart when they emitted their light, and the universe was only 380,000 years old at that time, how could they have the same temperature? Light from one region would have taken 84 million years to reach the other, more than 200 times longer than the universe had existed. These regions should never have been in causal contact, never able to exchange energy or information, never able to reach thermal equilibrium. Yet they display temperatures that match to within 0.001% live. This is like finding that two ovens in different galaxies, with no communication between them, maintain exactly the same temperature to within a fraction of a degree. In the language of physics, regions beyond each other's light horizons should not be causally connected. Yet the cosmic microwave background shows evidence of causal connection across the entire observable universe. This horizon problem becomes even more acute when we consider the cosmic microwave background's smoothness on all angular scales. Not only do opposite sides of the sky show the same temperature, but regions separated by any angle, 90 degrees, 45 degrees, even adjacent patches of sky, all show this remarkable uniformity. This suggests that the entire observable universe was in thermal equilibrium when the cosmic microwave background was emitted, despite consisting of regions that should never have been able to communicate. The standard Big Bang model, without additional assumptions, cannot explain this uniformity. If the universe expanded at a constant rate from the very beginning, different regions of the cosmos should show dramatic temperature differences based on their local conditions during the first 380,000 years. We should observe a cosmic microwave background that varies significantly across the sky, reflecting the chaotic, non-uniform conditions we'd expect in the early universe. The resolution to the horizon problem comes from the theory of cosmic inflation, proposed by Alan Guth in 1980. Inflation suggests that during the universe's first fraction of a second, specifically between about 10 circumflex 36 and 10 circumflex 32 seconds after the Big Bang, space underwent a period of exponential expansion, far more rapid than the expansion we observe today. During inflation, a region of space smaller than a proton expanded to astronomical size in an infinitesimally short time. This means that regions of the cosmic microwave background that appear to be causally disconnected were actually part of the same tiny thermally equilibrated patch of space before inflation began. They were in causal contact when the universe was much younger and smaller, achieved thermal equilibrium, and then were separated by the exponential expansion of inflation. Think of inflation like inflating a balloon with a detailed pattern painted on it. Before inflation, the entire pattern exists on a small surface where all parts are in contact. During inflation, the balloon expands rapidly, carrying different parts of the pattern far apart. From the perspective of observers on the inflated balloon, distant parts of the pattern appear to have no connection, yet they show coordinated features because they originated from the same small connected region. Inflation also explains the precise pattern of tiny temperature fluctuations observed in the cosmic microwave background. These fluctuations, varying by just a few millionths of a degree, represent quantum mechanical fluctuations that were stretched to cosmic scales during inflation. These primordial fluctuations became the gravitational seeds that eventually grew into galaxies, clusters, and the large-scale structure of the universe. The horizon problem reveals something profound about the relationship between observation and cosmic history. The uniformity we observe in the cosmic microwave background is not evidence that the early universe was naturally smooth and homogeneous, but rather evidence of a dramatic physical process, inflation, that created uniformity from what might have been chaotic initial conditions. This illustrates how ancient light can reveal not just what the universe looked like in the past, but also what physical processes must have occurred to create the conditions we observe. The 13.8 billion-year journey of cosmic microwave background photons carries encoded information about events that happened during the universe's first fraction of a second, events so brief and so early that they occurred before atoms, before nuclei, even before the fundamental forces of nature had separated into their current forms. The horizon problem also demonstrates that our observable universe preserves evidence of its own creation. In 1998, two independent teams of astronomers studying distant supernovae made a discovery that revolutionized our understanding of cosmic expansion and added a new layer of mystery to the ancient light reaching us from across the universe. They found that the expansion of space is not slowing down as expected, but actually accelerating. This acceleration is driven by dark energy, a mysterious component that makes up approximately 68% of the universe's total energy density and affects how we interpret the ancient light from distant cosmic objects. The discovery came from observations of Type I supernovae, white stellar explosions that serve as standard candles because they always reach roughly the same peak brightness. By comparing how bright these supernovae appear versus how bright they should be based on their distance, astronomers can measure cosmic expansion at different epochs in the universe's history. The ancient light from these distant stellar explosions, some from when the universe was only half its current age, revealed that cosmic expansion was slower in the past than it is today. This finding was completely unexpected. In a universe dominated by matter and radiation, gravity should be gradually slowing cosmic expansion over time. The mutual gravitational attraction between galaxies, clusters, and all forms of matter should be acting as a cosmic brake, decelerating expansion, even if it never stops entirely. Instead, the ancient light from distant supernovae revealed that something is causing expansion to speed up. Dark energy represents a form of energy that, unlike matter or radiation, doesn't dilute as the universe expands. While matter becomes less dense as space grows, the same amount of matter spread over more volume. Dark energy maintains constant density even as new space is created. This means that as the universe expands and matter becomes more dispersed, dark energy becomes increasingly dominant, driving acceleration. The effects of dark energy on ancient light are subtle but measurable. Photons, traveling through accelerating expansion, experience a slightly different journey than they would in a decelerating universe. The expansion history affects how much cosmic redshift accumulates during a photon's journey and influences the relationship between distance and recession velocity. This is why observations of distant supernovae could reveal acceleration. Their ancient light carries encoded information about the expansion rate when it was emitted. For the most ancient light we can observe, the cosmic microwave background, dark energy had minimal influence. When those photons were emitted 13.8 billion years ago, at that epoch, matter and radiation dominated the universe's energy density, and dark energy was negligible. But during the billions of years that cosmic microwave background photons have traveled toward us, dark energy has gradually taken control of cosmic expansion, accelerating the recession of distant objects. This transition from deceleration to acceleration occurred relatively recently in cosmic history, about 5 to 6 billion years ago, when the universe was roughly half its current age. Ancient light from galaxies at intermediate distances shows us the universe during this crucial transition period, preserving evidence of the moment when dark energy began to dominate cosmic evolution. The accelerating expansion driven by dark energy has profound implications for our cosmic future. Galaxies that are currently observable will eventually disappear beyond our cosmic horizon as acceleration carries them away faster than light. In the far future, trillions of years from now, observers in our local group will see a universe that appears nearly empty, with cosmic expansion having carried all other galaxies beyond the observable horizon. Dark energy also affects our interpretation of ancient light by changing the relationship between look-back time and distance. In a universe with dark energy acceleration, objects at a given distance are actually older than they would be in a universe with constant or decelerating expansion. This means that when we observe galaxies billions of light years away, We're seeing them at an even earlier stage of cosmic evolution than we might initially calculate. Perhaps most mysteriously, we still don't know what dark energy actually is. It might be a cosmological constant, an intrinsic property of space itself, as Einstein originally proposed and later called his greatest blunder. It might be a dynamic field that changes over time, similar to the field that drove cosmic inflation, but much weaker. Or it might be evidence that our understanding of gravity itself breaks down on cosmic scales, requiring modifications to Einstein's general relativity. The ancient light, carrying information about dark energy, represents one of astronomy's greatest detective stories. Hidden in the spectra of distant supernovae, encoded in the subtle patterns of galaxy clustering, and preserved in the journey times of ancient photons, are clues about the mysterious force that controls the universe's ultimate destiny. Dark energy ensures that the universe will continue expanding forever, eventually reaching a state of maximum entropy, where all stars have died, all black holes have evaporated, and space contains only a thin soup of elementary particles separated by ever-growing distances. So, the ancient light we observe today, from nearby stars to the cosmic microwave background, represents a temporary phenomenon in the universe's evolution, a brief epoch when matter was concentrated enough to form stars, galaxies, and observers capable of detecting the ancient photons traveling through the cosmos. Every photon reaching our telescopes is like a page from the universe's autobiography, carrying information not just about its source, but about the entire cosmic journey from emission to detection. This ancient light has written the universe's life story in wavelengths, spectral lines, and polarization patterns, creating a vast library of cosmic history that spans 13.8 billion years of evolution. The spectrum of ancient light reveals the chemical composition of distant objects with extraordinary precision. When starlight passes through a stellar atmosphere or interstellar gas, specific wavelengths are absorbed by different elements, creating dark absorption lines that serve as cosmic fingerprints. Hydrogen leaves its signature at precise wavelengths, as do helium, carbon, oxygen, and dozens of other elements. By analyzing these spectral features in ancient light, astronomers can determine not just what elements were present billions of years ago, but their relative abundances and physical conditions. This spectroscopic archaeology reveals the universe's chemical evolution over cosmic time. Light from the most distant galaxies shows lower abundances of heavy elements, reflecting an epoch when fewer generations of stars had lived and died to enrich the cosmic gas supply. Intermediate distance galaxies show the gradual buildup of elements like carbon, oxygen, and iron as stellar nucleosynthesis progressed. Nearby objects reveal the current state of cosmic chemical evolution, with heavy element abundances similar to our solar system. Ancient light also carries information about the physical conditions in distant objects, their temperatures, densities, magnetic field strengths, and states of motion. The Doppler effect shifts spectral lines based on motion toward or away from us, allowing astronomers to measure rotation rates of distant galaxies, orbital motions in binary star systems, and the expansion of the universe itself. Zeeman's splitting of spectral lines reveals magnetic field strengths in distant stars and galaxies. The width and shape of emission lines indicate gas temperatures and turbulence. Perhaps most remarkably, ancient light preserves information about cosmic processes that no longer occur in the nearby universe. The most distant galaxies show evidence of the first generation of star formation, when massive, metal-free stars created the first heavy elements in spectacular supernova. Quasars, powered by actively feeding supermassive black holes, were much more common in the distant universe, and their ancient light shows us galaxy formation and black hole growth during cosmic adolescence. The polarization of ancient light adds another layer of information about cosmic magnetic fields, scattering processes, and the geometry of distant objects. The cosmic microwave background shows subtle polarization patterns that reveal the universe's first magnetic fields and provide evidence for cosmic inflation. Polarized light from distant galaxies traces magnetic field structures that have evolved over billions of years. Ancient light also serves as a cosmic clock, allowing us to measure the ages of distant objects and trace their evolutionary histories. The colors of stellar populations change predictably as they age. Young, hot stars appear blue, while older populations become dominated by cooler, redder stars. By analyzing the colors and spectra of ancient light from distant galaxies, astronomers can determine when their stars formed and how their stellar populations have evolved. The journey of ancient light through expanding space adds temporal information that goes beyond the objects themselves. Cosmological redshift measures how much the universe has expanded since the light was emitted, providing direct evidence for cosmic expansion and allowing precise measurements of cosmic distances and ages. The accumulated effects of expansion on ancient light have revealed the universe's acceleration and the existence of dark energy. Even the absence of certain types of ancient light tells us important stories. The cosmic microwave background represents the oldest electromagnetic radiation we can observe because the universe was opaque to light at earlier times. This opacity boundary preserves information about the transition from the opaque early universe to the transparent cosmos we observe today. Ancient light has also revealed the universe's large-scale structure, the cosmic web of filaments and voids that emerged from tiny quantum fluctuations in the early universe. Galaxy surveys, using ancient light from billions of objects, have mapped this structure across cosmic history, showing how gravitational attraction has shaped the distribution of matter over billions of years. History, the universe's biography, written in ancient light, tells a story of continuous change and evolution, from the simple, smooth early cosmos to the complex structured universe we observe today. Each wavelength, each spectral line, each polarization measurement adds details to this cosmic narrative. Understanding the journey of ancient light across 13.8 billion years fundamentally transforms our perspective on humanity's place in the universe, not just in space, but in the vast sweep of cosmic time. We exist at a specific moment in the universe's 13.8 billion-year history, in a particular location within structures that have been evolving since the cosmos first became transparent. Our cosmic address includes not just where we are, but when we are in the universe's ongoing story. Our temporal address places us in what astronomers call the stelliferous era, the age of stars. We live during a relatively brief period in cosmic history when the universe contains the right conditions for stellar formation, planetary systems, and potentially life. The ancient light around us shows that we inhabit a universe roughly 13.8 billion years old, but stellar formation began only about 100 million years after the Big Bang, and it will cease in roughly 100 trillion years when the universe's gas supply is exhausted. From the perspective of cosmic time, we exist during the universe's prime, the era when galaxies are still forming stars, when supermassive black holes are actively growing, when cosmic expansion is transitioning from deceleration to acceleration. The ancient light we observe shows us that earlier epochs were more violent and chaotic, while future epochs will be increasingly cold and empty as expansion carries galaxies apart and stars exhaust their nuclear fuel. Our spatial cosmic address begins with Earth, orbiting the Sun in the habitable zone of a middle-aged G-type star. But the ancient light from distant objects puts this address in cosmic perspective. Our solar system formed 4.6 billion years ago in the disk of the Milky Way, about 26,000 light-years from the galactic center. The light from that galactic center shows us our cosmic downtown as it appeared when early humans were developing agriculture. The Milky Way itself occupies a suburban position in the local group, a collection of about 80 galaxies dominated by our galaxy in Andromeda. The ancient light from Andromeda shows us our largest neighbor as it appeared 2.5 million years ago, during humanity's evolutionary infancy. In 4.5 billion years, these galaxies will merge, fundamentally changing our cosmic neighborhood structure and completely altering the night sky visible to any future observers. Our local group belongs to the Virgo supercluster, a larger structure containing thousands of galaxies spread across 110 million light-years. But recent observations using ancient light from distant objects have revealed that we're part of an even larger structure, the Laniakea supercluster, containing over 100,000 galaxies across 520 million light-years. The ancient light from the edges of this cosmic neighborhood shows us regions as they appeared when complex life was just emerging on Earth. Yet even Laniakea represents just one small part of the cosmic web, the largest scale structure in the universe, consisting of vast filaments of matter separated by enormous voids. The ancient light from distant galaxy clusters shows us this web as it existed billions of years ago, when it was denser and more actively evolving than today. We inhabit a universe where matter is distributed in a complex, interconnected network that spans billions of light-years. Our cosmic address also includes our position in the observable universe, the sphere of space from which light has had time to reach us during the universe's 13.8 billion-year history. We sit at the center of this observable region, not because we occupy a special location, but because observation defines our perspective. Every observer in the universe sees themselves at the center of their own observable universe, bounded by their own cosmic microwave background horizon. The ancient light around us reveals that our observable universe contains approximately 2 trillion galaxies, each potentially hosting hundreds of billions of stars and trillions of planetary systems. This places Earth and humanity in a context of almost unimaginable cosmic abundance, while simultaneously emphasizing our isolation. The nearest potentially habitable planets are likely years to decades away at light speed, and communication with any alien civilizations would face delays measured in years or centuries. Our temporal cosmic address also reveals that we live during a unique epoch in the universe's history, the brief period when intelligent observers can study the cosmos. The ancient light we observe today will continue to fade as cosmic expansion carries distant galaxies beyond our observational horizon. Future observers will see a progressively emptier universe, eventually losing access to the ancient light that tells us about cosmic expansion, the Big Bang, and the universe's evolution. We also exist during the only era when the cosmic microwave background is observable with technology. In the distant future, this ancient light will be redshifted beyond detection, and in the distant past, the universe was too hot and dense for observers to exist. We inhabit a narrow window of cosmic time, during which the universe's story can be read in ancient light. Perhaps most remarkably, our cosmic address places us in an era when the universe has evolved sufficient complexity to produce observers capable of studying their own cosmic context. The same stellar nucleosynthesis that enriched the universe with heavy elements also created the carbon, oxygen, and other elements essential for biology and consciousness. We are literally made from recycled starlight, atoms forged in stellar cores billions of years ago, scattered by supernova, and eventually incorporated into our solar system and bodies. The ancient light surrounding us connects us to this vast cosmic heritage, reminding us that our existence depends on 13.8 billion years of cosmic evolution. As we stand on the threshold of a new era in astronomy, revolutionary telescopes and detection technologies are preparing to capture even more ancient light, potentially revealing cosmic epochs that have never been observed before. These future observations will push the boundaries of our cosmic archaeology, uncovering new chapters in the universe's biography and possibly answering fundamental questions about cosmic origins, the nature of dark matter and dark energy, and the prevalence of life throughout the cosmos. The James Webb Space Telescope, humanity's most powerful cosmic observatory, is already transforming our understanding of the early universe by detecting ancient light from galaxies that formed just 400–600 million years after the Big Bang. Operating primarily in infrared wavelengths, JWST can observe the highly redshifted light from these primordial galaxies with unprecedented clarity, revealing their structure, composition, and star formation processes during cosmic dawn. Early observations have already shown that galaxies in the early universe were more massive and mature than theoretical models predicted, suggesting that cosmic structure formation proceeded more rapidly than we previously understood. But JWST is just the beginning. The next generation of ground-based telescopes, including the Extremely Large Telescope, ELT, with its 39-meter mirror, and the 30-meter telescope, TMT, will collect ancient light with unprecedented sensitivity and resolution. These instruments will be capable of directly imaging potentially habitable planets around nearby stars and analyzing their atmospheric composition through ancient light that has interacted with alien atmospheres. For the first time, we may be able to detect biosignatures, chemical evidence of life in the ancient light from other worlds. Future space missions will push even deeper into cosmic time. Proposed observatories designed to study the cosmic microwave background with greater precision may reveal evidence of cosmic inflation in the form of primordial gravitational waves, which would appear as subtle polarization patterns in the universe's oldest light. The observatories designed to study the cosmic microwave background. The observatories designed to study the cosmic microwave background with greater precision may reveal evidence of cosmic inflation in the form of primordial gravitational waves, which would appear as subtle polarization patterns in the universe's oldest light. These observations could provide our first direct evidence of the physical processes that occurred during the universe's first fraction of a second. Next-generation gravitational wave detectors will add an entirely new dimension to our study of ancient cosmic events. While electromagnetic light becomes increasingly difficult to observe at the greatest distances due to cosmic expansion and intervening matter, gravitational waves travel through the universe, essentially unimpeded. Space-based gravitational wave observatories, like LISA, Laser Interferometer Space Antenna, will detect the ancient gravitational waves from massive black hole mergers that occurred billions of years ago, providing information about cosmic epochs that are challenging to study through electromagnetic radiation alone. The combination of electromagnetic and gravitational wave astronomy will create multi-messenger observations of ancient cosmic events, allowing us to study the same phenomena through different types of information carriers. Ancient light will tell us about the electromagnetic signatures of distant events, while ancient gravitational waves will reveal their gravitational and kinematic properties. Together, these observations will provide a more complete picture of cosmic evolution than either could achieve alone. Future neutrino detectors may also contribute to our understanding of ancient cosmic processes. Neutrinos, which interact so weakly with matter that they can travel through the universe essentially unchanged, carry information about high-energy processes in distant objects. Ancient neutrinos from stellar collapse, active galactic nuclei, and other violent cosmic phenomena may provide insights into the universe's history that complement what we learn from ancient light. One of the most exciting frontiers involves searching for ancient light from the universe's very first stars, the so-called population 3 stars that formed from primordial gas containing only hydrogen and helium. These massive metal-free stars would have been fundamentally different from any stars we observe today, and their death in spectacular supernovae created the first heavy elements in the universe. Advanced infrared telescopes may eventually detect the ancient light from these primordial stellar explosions, showing us the moment when cosmic chemical evolution began. Future observations of ancient light may also reveal new insights about dark matter and dark energy. Precision measurements of the cosmic microwave background's polarization patterns could provide evidence for dark matter's particle properties through subtle effects on the early universe's evolution. Observations of distant supernovae and galaxy clusters will trace dark energy's influence over cosmic history with increasing accuracy, potentially revealing whether dark energy is truly constant or changes over time. The search for ancient light from potentially habitable planets represents one of the most profound frontiers in astronomy. Future telescopes, designed specifically for exoplanet studies, will analyze starlight filtered through alien atmospheres, searching for the chemical signatures of water vapor, oxygen, methane, and other molecules that might indicate biological activity. The ancient light from these distant worlds, photons that last interacted with alien atmospheres years, decades, or centuries ago, may provide our first evidence of life beyond Earth. Advanced artificial intelligence and machine learning algorithms will revolutionize how we analyze ancient light. These computational tools will be capable of identifying subtle patterns in vast datasets that human analysts might miss, potentially discovering new types of cosmic objects, unexpected correlations in cosmic evolution, or previously unknown physical processes preserved in ancient photons. Future observations will also address fundamental questions about the universe's ultimate fate. As our measurements of cosmic expansion become more precise, we'll better understand whether the universe will continue expanding forever, eventually contracting in a big crunch, or undergoing some other destiny. Ancient light from increasingly distant objects will map the history of cosmic expansion with unprecedented accuracy, revealing how dark energy has influenced cosmic evolution over time. Perhaps most remarkably, future technology may eventually allow us to observe cosmic epochs that are currently beyond our reach. Proposed concepts for observatories positioned at the sun's gravitational focus could use our star as a giant gravitational lens, potentially magnifying ancient light from extremely distant objects and revealing cosmic structure formation during previously unobservable epochs. The ancient light that has traveled billions of years to reach us represents just a fraction of the information the universe has preserved about its own history. As our instruments become more sensitive and our analysis techniques more sophisticated, continue decoding new chapters of the cosmic story written in the wavelengths, polarizations, and arrival times of ancient photons. The universe's biography, recorded in the ancient light surrounding us, is far from complete. Each new observation adds pages to this cosmic narrative, and the most exciting discoveries may still lie ahead, hidden in ancient light that has been traveling toward us since the universe's youth, waiting for the right technology and the right questions to reveal their secrets. We began this journey with light traveling at 299,792,458 meters per second, circling Earth in the blink of an eye. We end it with the realization that this same light, the fastest thing in the universe, takes 13.8 billion years to carry news from the cosmos's birth to our eyes. The ancient light surrounding us tells the ultimate story. Every photon is a messenger from the past. Every star shows us yesterday. Every galaxy reveals antiquity. The cosmic microwave background delivers the universe's first words. This ancient light reveals distances so vast they dwarf human comprehension. Our observable universe spans 93 billion light-years. Yet this unimaginable scale pales beside an even more staggering truth. We exist during the narrow window of cosmic time when this ancient light remains visible. In the far future, cosmic expansion will carry these distant beacons beyond our horizon forever. The light we observe today represents a temporary gift from the cosmos. The universe's expansion ensures that future observers will inherit an increasingly empty sky. The ancient light that connects us to cosmic history will fade as space itself grows between us and the distant sources of illumination. We live during the universe's brief moment of maximum visibility. The cosmic web reveals itself through ancient photons. Galaxy clusters preserve their evolutionary history in redshifted light. The cosmic microwave background glows with the afterglow of creation itself. Yet this ancient light also points toward futures we cannot observe directly. The galaxies we see, formed when the universe was young, will continue evolving long after their current light reaches us. Stars being born in distant nebulae today will live and die in cosmic isolation. The universe's story continues beyond what any observer can witness. In the end, ancient light teaches us that we are both central and peripheral to cosmic evolution. Central because we occupy the observational center of our own observable universe. Peripheral because we exist for an infinitesimal fraction of cosmic time in an unremarkable region of an ordinary galaxy among trillions. The 13.8 billion year journey of ancient light reminds us that we are temporary participants in an eternal cosmic story, witnesses to an unimaginably vast and ancient universe that has been writing its autobiography in light since the moment it first became transparent to its own illumination. What strikes you most about this cosmic journey through deep time and deeper space? I'd love to hear your thoughts about which moment in this 13.8-billion-year story resonates most powerfully with you. Thank you for joining me on this expedition across the universe's history written in ancient light. If this journey through cosmic time has sparked your curiosity about our place in the vast cosmos, I'd be grateful if you'd like this video and subscribe to continue exploring these cosmic mysteries together. The universe holds countless more stories waiting to be discovered in the ancient light streaming toward us from every direction in space and time. Ready to explore another cosmic mystery? Our channel contains an entire collection of deep space documentaries that will take you even further into the universe's most extraordinary secrets and surprising revelations.